Good morning. So in this section, we're going to talk about what strategy should the players employ in a two-person's game to maximize the payoff, to minimize the loss, or to maximize the payoff in general. And we're talking about mixed strategies for non-strictly determined games. Remember from a previous section that if the game is strictly determined, there is not much discussion in terms of the strategy. One player will choose exactly a precise row or a precise column because that will always be the best choice in a strictly determined game. Now I want to make it clear what we mean by strategy here in the language of probability, basically. So if the game is not strictly determined, then we could choose to each player can choose to employ or to choose different rows and columns with some frequency. So by strategy, we mean the frequency of choosing rows for player 1 and columns for player 2 according to a probability distribution. All right, so let's make it even clearer. We'll talk about this example. So let's say player 1, which plays the row, remember? So player 1 will choose each row equally likely. So that means, so we will describe this with a row matrix, which in this case is going to be 1/2, 1/2. So if that player 1, will want to choose either row 1 or row 2 equally likely, that means there's a 1/2% or 50% probability of choosing row 1, 50% probability of choosing row 2, 50-50, right? So he will choose row 1 with probability 1/2, row 2 with probability 1/2. So this strategy can be illustrated or denoted in, not denoted, can be written in terms of a row matrix. It's either a row or a column. It's going to be a column matrix for the second player. That's just for the reason of being in agreement with the way we compute multiplication of matrices. You will see later. Conceptually, it doesn't matter as much, right? It's going to be either a row or a column matrix because you indicate a certain strategy. And remember, the entries should add up to 1 always, no matter what the strategy is, because each time you play the game, or the player plays the game, then the choice is to choose one of the two rows. So no matter what the frequency is for each of the rows, the two probabilities should add up to 1. And let's say in the same game, player 2 wants to choose column 2 twice as likely, or twice as often, let's say it like that, twice as often. That means the strategy is gonna be 1/3, 2/3, and we're gonna denote that with a column matrix. So the strategy of player 2 will always be a column matrix. The strategy of player 1 will be a row matrix. But again, make sure you understand the meaning of the entries. So if you decide, or if the player 2 decides to choose column 2 twice as often, that means in order to add up to 1, the probability distribution should be 1/3, 2/3. And the question is, if they employ this strategy, what is the payoff? So let's look at an example. And to make it a little bit more general, and we'll go back to these strategies, 1/2, 1/2, 1/3, 2/3. Let's say more generally, that strategy of player 1 is big P equals P1, P2, little P1 and little P2. These are the probabilities of choosing row 1 and row 2. And also it will be in agreement with the formula sheet. That's why I'm using this notation. So again, remember P1 plus P2 must be equal to 1, right? Because these are probabilities that add up to 1. And let's say also that the strategy of player 2 is denoted by big Q, and it's going to be a column matrix Q1 and Q2 with little q1, little q2 equals 1, just like P1 and P2. So the question now, what is the payoff expected payoff for each strategy, assuming that we play this game repeatedly? And we illustrate this with an example. So suppose the payoff matrix A is given by the entries 4, minus 1, minus 3, and 6. Okay, so let's talk about player 1 first, right? So player 1 will choose either row 1 and column 1 with probabilities P1 and P2. So row 1 with probability P1, row 2 with probability P2. Now, player 2 will respond with choosing either column 1 or column 2. Okay, what happens from the point of view of player 1 if column 1 is chosen? Well, then the payoff are 4 and minus 3. And remember from the probability theory, from the expected value, you may want to look back at the section on expected value. The expected value in this case is going to be the sum of the payoffs, the sum of the products between the payoff and its probability. So if player 1 will choose, if player 2 will choose column 1, then there will be $4 payoff with probability P1, so multiply by P1, plus minus $3 payoff, so that's going to be a loss, obviously, times probability P2. So it's going to be 4P1 minus 3P2. If the player 2 will choose column 2, then in that case it's going to be a loss of $1 minus $1 with again probability P1 plus $6 times probability P2. So that's going to be minus P1 plus 6P2. So from the point of view of player 1, if player 1 employs this strategy, P1 and P2, then the expected payoff, depending on the response of player 2, will be 4P1 minus 3P2 or minus P1 plus 6P2. So you can see already that you can tweak these numbers, the strategies, the probability is thinking in terms of how the other player responds. So for example, if you think player 2 has a propensity of choosing column 2, you probably want to have a strategy that makes probability P2 much bigger than P1. You will choose, for example, P1 1 over 10, P2 9 over 10. Now remember, this is a two-person's game. The other player will also have his own strategy in response to you. But the point is that it all depends on what the other player does. These are the expected values if you have your strategy, and then depending on what the other player will choose. Now, very important here to make use of the formulas. Notice that this expected value can actually be written in terms of a matrix product. Let's write actually here on the left. You may write it down again if you don't have room. You can actually multiply the row matrix P1, P2 with the payoff matrix 4, minus 1, minus 3, and 6. So please check the matrix multiplication to convince yourself that this is a valid matrix multiplication. You multiply a 1 by 2 matrix, 1 row, 2 columns, with a 2 by 2 matrix, and the answer, of course, is 1 by 2. P1 times 4 minus 3P2, P1 times minus 1 plus 6P2. This is because in the formula sheet, we're going to denote the payoff, the expected payoff for player 1 as P times A. P is the row vector, the row matrix, and A is the payoff matrix. We're going to write down the formula immediately. So let's do the same thing now from the point of view of player 2. Now player 2, remember, has the strategy of choosing either column 1. Let's write again the payoff matrix here. So the player 2 will choose column 1 with probability Q1, column 2 with probability Q2. Player 1 will respond, right, with choosing row 1 and row 2. So if player 1 chooses row 1, well, the payoffs are 4 and minus 3 with probabilities, let's see, 4 and minus, I have the same thing, 4 minus 1, minus P1 plus 6P2. So column 1, looking at, so I was looking at the wrong thing. So if player 1 will choose row 1, then the payoffs are going to be 4 and minus 1. 4 and minus 1 is with probabilities Q1 and Q2. So therefore you have $4 times Q1 plus minus $1 times Q2. That's 4Q1 minus Q2. If player 1 will choose row 2, then the payoffs are minus 3 and 6, depending on the columns that the player 2 will choose. So that's going to be minus $3 payoff times Q1 plus $6 payoff times Q2. And that's going to give me minus 3 Q1 plus 6 Q2. This quantity as well can be written nicely in terms of matrix multiplication. If you look carefully here, you can write this as a product between the payoff matrix. Let's see if we can squeeze it here. 4 minus 1 minus 3 and 6. And the column representing the strategy of the second player. So basically in this case, the expected payoff of player 2 is going to be A times Q in this order, right? By big Q, remember we mean the strategy, the column matrix representing the strategy of player 2. So we're going to write another example immediately. I mean, the examples I started with 1/2, 1/2, and 1/3, 2/3 on the second page. After we write the formula. So one last remark, one additional remark, and then a formula, and then we're gonna finish off with some other examples. So stay tuned for the second page. All right, so to fix our ideas, remember the payoff matrix is denoted by A. In our case, A was, in our example, A was 4 minus 1 minus 3 and 6. And the strategy for player 1 was given in a row matrix, P1, P2, the strategy of player 2 in a column matrix, Q1 and Q2. So what we established, and let's write it down here, is that the expected value, the expected payoff of player 1 is P times A. The expected payoff of player 2 is A times Q. So this is basically to make it shorter as a formula so that you don't have to do the whole analysis for every matrix. You just basically compute this multiplication, and that's the answer for the expected payoff for each strategy. One last thing, one last important quantity here. So notice that the two players employ their own strategies, right? They choose the rows and columns with a certain frequency. That means each entry, which is each payoff, is chosen with a certain probability coming from the two strategies. So remember, row 1, column 1 is independently chosen by the two players according to probabilities P1 and Q1, right? So the overall probability of actually obtaining that payoff is basically the product of probability P1 and Q1, right? Remember, when you have independent events, you multiply the probabilities. So row 1 and column 1, which gives you the payoff 4, that comes from probability P1 times Q1, because that's the strategy employed by the two players. Consequently, the payoff minus $1 is chosen with probability P1 Q2, row 1, column 2. Finally, plus payoff minus $3, that comes from P2 Q1, and then finally $6 is chosen with probability P2 and Q2. If you do the matrix multiplication carefully, you will realize that this quantity is also given in a more compact form by P times A times Q. So you can write it here on the left corner, that, and this is basically the value of the game. The expected payoff for coming from the two mixed strategies. So to summarize, payoff for player 1 is gonna be a row matrix from P times A. Payoff for player 2 is gonna be A times Q. The value of the game is gonna be P times A times Q. So everything is combined essentially into 3 matrix multiplications, which is rather nice in a compact form, so to speak. Okay, so let's illustrate this with a couple of examples. We're going to start with the first example when I said, what if player 1 wants to choose row 1 and row 2 equally likely, 50-50? Remember, you always represent the strategy of player 1 by a row vector. Player 2 will employ the strategy of choosing column 2 twice as likely, so that's going to be 1/3, 2/3. And now let's just compute the expected values or payoffs for each strategy. So for expected value of, or expected payoff of player 1, that's going to be P times A. Here again, you have to make sure you compute the matrix multiplication correctly. And remember, that gives you 1 row, 2 columns. So that's going to be 1/2 times 4 plus 1/2 times minus 3. 1/2 times minus 1 plus 1/2 times 6. And that's going to be 4/2, which is 2. What is that? Minus 3/2. That's going to be 1/2. And that's going to be 6 minus 1/2. That's 5/2. So obviously, in this strategy, player 1 hopes player 2 will choose column 2 more often. I hope that makes sense, right? Because these two expected payoffs are what you get in response to player 2, who will choose either column 1 or column 2. What about the expected payoff of the second player? That's going to be A times Q. That's a 2 by 2 matrix, the same payoff matrix, times the column matrix 1/3, 2/3. Remember, for matrix multiplications, multiply 2 by 2 with 2 by 1, that gives you another column matrix. So the payoff of the second player will be in the form of a column matrix. 4 times 1/3, minus 1 times 2/3, minus 3 times 1/3, plus 6 times 2/3. 4/3 minus 2/3, that's 2/3. Minus 3 plus 12 makes it 9/3, that's 3. You can pause for a moment and ask yourself, what does player 2 hope player 1 does more often? Choosing row 1 or row 2. So by employing this strategy, I hope you answered that player 2 hopes player 1 will choose row 2 more often, because in that case you will get he will get a bigger payoff. So this begs the question, by the way, and that's going to be the culmination of our course, last section, which will come up after this section. Is there a strategy, the best strategy for one of them, for each player, so that no matter what the opponent does, I'll get the best possible outcome? So the best outcome that is independent on the choice of the opponent. And you will see that there is such an answer as we see in the last part of the course, right? The last section. The value of the game is an overall assessment of whether these strategies favor one player or another, right? So the value of the game is going to be PAQ. When you do this, by the way, remember half of it is already done, right? So P times A, it's already computed. 1/2, 5/2, that's a row matrix, times Q, which remember is a column matrix. So if you multiply a 1 by 2 matrix with a 2 by 1 matrix, you get the 1 by 1 matrix, which is basically a real number. So 1/2 times 1/3 plus 5/2 times 2/3. That's going to be 1 plus 10/6. I didn't have the calculator with me here. 4 minus 1 minus 3, 6. No, not sorry, 11/6. Yeah, and we'll leave it at that. 11/6. So that means basically this strategy is in favor of player 1 because it's positive, right? So remember, positive means we get different. Positive means that player 1 gets paid. And I'm going to go over another example on a short second page just to see that employing different strategy for the same game will obviously result in a strategy that is in favor of the other player, for example. So stay tuned for a short, quick extra example before we call it a day. All right, so what if player 1 wants to choose row 2 more often? Let's say the probability distribution is 1/5, 4/5. That means row 2 in that example is chosen 4 times more often. And what if probability the player 2 will choose column 1 3 times more often? Okay, what happens in that case? Again, for the same payoff matrix, which was 4 minus 1 minus 3 and 6. In the previous strategy, remember that was favoring player 1 because it was a positive payoff. So let's compute the value of the game, PAQ. 1/4, 5, 4/5 times the payoff matrix 3/4, 1/4. There are 2 multiplications, so you have to perform them one by one. The first one gives you a row matrix, 1/5 times 4 plus 4/5 times minus 3. 1 over 5 times minus 1 plus 4 over 5 times 6, to which we're going to multiply to 3 over 4, 1 over 4. 4 minus 12, that's going to be minus 8 over 5. 24 minus 1 on the top here, that's 23 over 5. So notice that for sure this player hopes that second player chooses column 2 more often, because that's when you have positive outcome. 3 over 10, then you multiply this by the column matrix, 3 over 4, 1 over 4. And finally that gives you minus 8 over 5 times 3 over 4 plus 23 over 5 times 1 over 4. So that's going to be minus 24 plus 23 over 20 minus 1 over 20, which is less than 0. So this strategy favors player 2. So you may wonder, before we call it a day, now how come there is such a thing as an optimal strategy? Because how am I supposed to choose the optimal for me if the other player, I don't know what he's going to do, right? The other player is going to choose a different strategy. But that is the key thing. Rather than anticipating what the other player does, because again, this is not a strictly determined game. There's no such thing as a rational decision all the time to choose either one row or the other. There's going to be some sort of frequency of choosing either of the two options. There is such a thing as a strategy that is basically independent of the choice given by the opponent, and that's true for both of them. So that's going to be basically the ideal situation in this kind of conflict. Now that doesn't mean that both of them will win or both of them will lose. That's going to be depending on the payoffs, right? Depending on the actual entries in the payoff matrix, but is the best given the available payoffs. So for example, if it's negative, if the optimal strategy is going to be negative for player 1, that means for that particular payoff distribution, for that particular game, the player 1 can only minimize his losses, essentially. So that's the best strategy independent of what the other person does, although it's still a loss, right? But that's because of the payoffs in the matrix. So that's it for today. We're gonna finally meet next time for the last section, which will be the nicest one, I think, in this chapter. So stay tuned for, not stay tuned. I'll see you next time.